Okay, so on this one, a meter stick of negligible mass is placed on a fulcrum. That means a pivot point at the 0.4 meter mark. That is 4 centimeters. Think of it like change, in case you've forgotten, like, hey, what's that? 40 cents, 40 centimeters. Okay, so here we go. We got 40 or 0.4 meters on this side. This is where it's going to be rotating around. Okay, and that means you got 0.6 meters on this side. All right, so let's see. A 5 kilogram mass is hung at the 1 meter mark. So I'm guessing that's right here. So that's 0.5 kilograms. So that means, by the way, that the weight of this is going to be 5 newtons. I'm just gonna, that's not a very good picture, but it's right here. That's at the end of the meter stick. And on the other side, you have 1 kilogram, which that's the weight of that one's going to be 10 newtons. Okay, so let's look at your torques. So your torque this way, your force is going to be the weight. So the torque this way is going to be the weight times the fulcrum, because remember, torque is just R cross F, and we're going straight line, so it's just R times F. So this is your R right here, distance from the center. Okay, so that's 0.4 times 10, so that's going to be 4 Newton meters. Remember, we don't do joules for this. This is Newton meters because torque is different. And on this side, that's going to be 0.6 times 5. That's going to give you, you can put this in the calculator if you want, 3 Newton meters. So let's look at your net torque. It's going to be heavier this way, so things are going to rotate this way in a positive or counterclockwise direction. And that's going to give you a net torque of 4 minus 3, 4 minus 3, which is going to give you 1 Newton meter, which is A. The answer to this one is A. I'm getting faster. All right, so let's look at 30. An object undergoes, this one's a little more in depth, an object undergoes simple harmonic motion along the x-axis as shown above, where x is 0, okay, is the object's equilibrium position, which is the following graphs. Okay, let's just kind of unpack that really quickly. Think of it this way. Frictionless surface, you got a wall, okay, you got a spring attached to it, right? Okay, and the spring's just kind of hanging out here, right? Okay, so, and then that spring also happens to have a mass that is attached to it. All right, so then let's look at this. If I bring this out to some spring displacement right here, right? So I've displaced it in the positive direction. What force is it going to be feeling? It's going to be feeling a restoring force that way, which means the acceleration goes that way in the negative direction. So when your acceleration is negative, or when your, let's look at this, when your displacement is positive, so when your displacement is on this part of the graph, then the acceleration needs to be negative. So it needs to be in the bottom part of the graph. Okay, and so let's look what happens afterwards. So when the spring pulls this back past the equilibrium position, back up here, and you have x in this direction, so you have a negative x, right? It's going to be going back this way. It's going to be accelerating back in that direction. So I kind of gave it away here. You've got positive position, this part, right? That means you're going to have negative acceleration, this part, so it's going to be in this quadrant. And then vice versa on the other one. It's going to be just the opposite. Whenever you're going to need to have a positive acceleration, we're not looking at the slope, we're just looking at, we're not looking at like, derivative, second derivative, whatever, integral. We're just looking at like what this actually says. So when it's positive, when you have a negative position, which will be this part of the graph, your acceleration needs to be up here. So the answer is A to this one as well.